Niels Bohr's model of the atom, in which the electrons orbited the nucleus much like the planets orbit the sun, hence the name the planetary atomic model, was based on the idea that the electrons were on a set, rigid path, kind of like a railroad track, and that they didn't deviate from this path, and that was the constant position or distance that they were at as they orbited the nucleus. And this presents some problems because electrons, being like charged particles, as they orbited the nucleus, if they would come in close proximity to one another, there'd be a drastic increase in the repulsive force, which would tend to want to push them off of that track. So another idea was put forth by a scientist by the name of Erwin Schrodinger, and he had an equation that would allow him to determine or calculate what distance from the nucleus you would most likely be able to find an electron present at. And really the only type of atomic model that you could solve Schrodinger's equation for exactly was a single electron atom, namely like a hydrogen atom. But as soon as you introduce multiple electrons, because of those repulsive forces, things got a lot trickier. So really the product of Schrodinger's wave equation, as it's referred to, is a number less than 1. And what it does is it gives you a probability. The closer to 1 the value is, then that distance that is plugged into the Schrodinger's wave equation is a high probability distance that you would find an electron at that location, or that distance at least from the nucleus. So this idea of the electron shells becomes a little more cloudy, if you will, because it's more of an idea of points of where you're most likely to find the shell that represents where you're most likely to find an electron. And if you were to solve Schrodinger's wave equation for distances in all 3 dimensions, what you would get if you were to plot all those points would be these electron clouds, these kind of nebulous, vague areas where we expect to find an electron. And so it can be useful to think about these clouds as things like other materials that we're experienced with that move at high speeds. The electrons are going to be moving extremely fast. And so you think about a fan. All right, when the fan is stopped, you can see the individual blades, you can see the particles, but as soon as it starts moving, you lose sight of that, and you get kind of this cloudy, nebulous area where you know the blades are at, but you can't pinpoint exactly where they are at any given time. And the electrons are the same sort of way in this idea of electron clouds. Now, with the Bohr model, we had this idea of rings around the nucleus, and those were the orbits that these electrons were traveling in. And to an extent, you know, that model still works. Those would be your main energy levels. But with the different transitions and the different frequencies of light that can be emitted in an emission spectra, just having, you know, 6 or 7 main energy levels wasn't going to be enough. There was the need for these intermediate energies, and so those main energy levels are further subdivided into sublevels, and the sublevels are designated with letters, and from low energy to high energy they run S, that followed by the P sublevels. After P you get the D sublevels and the F sublevels for the 4th one. And currently, with the elements that we have and their electron needs for filling in around the nucleus, that's all we have need for. As new elements are discovered, should it become necessary for a 5th sublevel, then we'll add on from there. Now, within these sublevels, there are individual compartments, if you will, that the electrons will reside in. And these compartments are known as orbitals. Now, the different sublevels contain a different capacity for each one. S sublevels are going to be able to hold 1 pair of electron, so they're going to have 1 orbital, and hence be able to hold a total of 2 electrons. P sublevels have 3 orbitals, 3 pairs of electrons, grand total of 6. D sublevels have 5 orbitals. 5 pairs of electrons they can hold, maximum of 10. Hopefully you're seeing a pattern here, and if you are going to make a prediction here, F sublevels can hold, hopefully you guessed it, 7 pairs of electrons. They have 7 orbitals for a grand total of 14. Now, these different orbitals, because they represent sublevels, all right, and the sublevels are part of the main energy levels, but just like the main energy levels are usually represented by rings at set distances, these sublevels would be like intermediate rings, if you will, okay, offshoots of those main rings. But herein lies the issue. Within those sublevels, all of the individual compartments, the orbitals, are at those same energy levels. So for something like an S sublevel, where you have just 1 pair of electrons, it's pretty simple. Getting 2 in an orientation where they're going to minimally interact, it's not that difficult. But compare that to, say, an F sublevel with its 7 orbitals. Now we've got a big issue, because now you're trying to get 14 electrons in the same energy sublevel, the same distance from the nucleus, and you need to get them all in there so that they're going to be somewhat stable. That's not exactly easy to do. And so what this leads to is the electron clouds taking on some pretty odd shapes. So the type of sublevel and the type of orbital is going to determine the shape, whereas the main energy level is going to determine the size of the cloud. And even the orientation, where these clouds sit in three-dimensional space and how they're arranged, is also dependent on, or something that we need to consider with the different orbitals. All right, so N, that's typically what we use to refer to as our main energy level. That's the main ring. What's going to affect the shape and the size? Size is mainly affected by the main energy level. The shape is going to be affected by the electron repulsions that are experienced by the various electrons filling in however many orbitals that sublevel has. Now, as I said, with S sublevels, you have a fairly simple, straightforward shape. It's a spherical shape because you only have 2 electrons and they're 180 degrees from each other, so you get this nice spherical cloud, what we typically think of in an electron cloud. That cloud, all right, if we think about it on an axis, at the origin of this XYZ axis that you see is where the nucleus would be. So your S orbital, your S electron cloud, is always centered about the nucleus, as is true of all of these orbitals. The P sublevel, if you remember, has 3 orbitals, so you need to get 6 electrons around the same nucleus in a manner that they are going to minimally interact with one another. And so what this does is it distorts the electron cloud, and based in part on Schrodinger's wave equation, the predicted cloud of highest probability of finding an electron creates a dumbbell shape. Now, you've got 3 orbitals, so you've got 3 dumbbell-shaped electron clouds, and the way that they orient themselves to one another to minimize that interaction would be 90 degrees to one another. So what you get for P orbitals are these dumbbell-shaped clouds, one lying directly on one on the y-axis, one on the x-axis, and then one on the z-axis. And so you get this, it's no longer a flat diagram. You have to imagine these dumbbell shaped clouds coming out of the screen at you and going back into the screen. And that's why you have this three-dimensional axis with the angled z-axis. Imagine it coming straight out and going straight back into the screen rather than being on an angle. If we continue and we think of D sublevels, they get even stranger. Now you've got to get 10 electrons about the same nucleus, so now you still have the dumbbell-shaped orbitals, but it's usually a double set of dumbbells, and they orient themselves between the axes. And then Fs just get even more bizarre looking, given that you're trying to get 14 electrons around them. So quite often we don't deal too much with Ds and Fs, rarely Fs. Ds sometimes, but S and P orbital clouds are pretty frequent ones that we encounter and we think about and describe.